In this video, we're going to look at conditional probability and dependent events. So conditional probability is given by this equation here. This is the probability that event B occurs given that event A has already occurred. And we find that by determining the probability of the two events happening, or the intersection of those two sets, divided by the probability of event A. So what it's like you're doing is you're restricting your sample space to be only that of event A, and then you are further determining that probability based on the amount of times that B and A happen, or the chance that those two events are going to happen together. So for example, here, data that they are probably collecting right now. In a recent medical survey of 100 randomly selected people in Cambridge, 38 people had a cough, 51 people had runny noses, and 9 people had both. So the first thing that we want to do is find the probability that a person had a runny nose given that they had a cough. So we'll set up our conditional probability equation. So runny nose given that they had a cough. Now what we need to determine is the probability that those two events happened together. And we're going to divide by our number of people that had runny noses. So the people that had a runny nose and a cough would be 9 out of 100. And the probability that someone had a, this should be cough here, because that is the event that's already occurred. So on the top, we've got 9 out of 100. That was the number of people that had both. On the bottom, we've got the probability that someone had a cough. So that would be 38 out of 100 people. Simplifying that is going to give us 9 out of 38, which is the chance that a person had a runny nose given that they had a cough. Another example of conditional probability here is we're going to find the probability that they had a runny nose given that they had no cough. So that means that on top, we would have the probability of those two events occurring together. So we've got runny nose and no cough over the probability that someone didn't have a cough. So the number of people that were runny nose and no cough would be, if you picture a Venn diagram, so we've got runny nose, cough. We are looking for the people that are in this blue section here. So in order to find that, we would take our total number of people that had a runny nose and subtract the number of people that had both. On the bottom, we're going to do sort of almost the same thing. The people that had no cough are the people that are outside this Venn diagram. So everywhere except the intersection and the cough only circle. So in order to find that, we can do 100 minus 38. So that's using our complement property, essentially. And then we can put those into our equation. So we've got 51 minus 9 out of 100 people over 100 minus 38 out of 100 people. Simplifying that is going to give us 42 over 62, which gives us a probability of 21 over 31. Or about 2/3 of the people had a runny nose with no cough. Our last example that we're going to do for conditional probability is 2 dice are rolled and the number on the up face is observed. We want to find the probability that one die shows a 5, given that the sum of the dice is 7. So probability that we got 1 5, given that the sum is 7. So on the top, we need 1 5 and we have the sum of 7. What is the chance of that occurring? And on the bottom, we want to know how many ways we can get a sum of 7. So if you think back to your dice roll chart, there are 2 ways that you can have a sum of 7 with 1 5 out of a possible 36 options. The number of ways that you can get a sum of 7 is 6 out of 36, actually the highest of any sums, which is one of the reasons why it's the lucky number 7. We can simplify this to 2/6 or 1/3. So you've got about a 33% chance of getting 1 5, given that your sum of the 2 dice is 7. In this video, we're also going to explore the idea of dependent events, which is where the occurrence of one event changes the probability of the following event. So in this example, this is one standard example of dependent events. So a card is drawn from a deck, and then another card is drawn without replacing the first. So your number of possibilities change in your second event based on what happened in the first event. So the probability that they are both red is going to be multiplying the probability of the action that you get a red card on the first draw times the fact that you get a red card on the second draw. So on the first draw, half of the cards in the deck are red. So you've got 26 possibilities out of 52 cards. Now on your second one, because you haven't replaced your first card, now you only have 51 cards to choose from. And if you've already chosen a red, then you only have 25 possible red cards to choose from. Multiplying these out would give us, 1/2 times 25 over 51, which would be 25 over 102, which is approximately a quarter. So about 25% chance that they are both going to be red. Next example here is the first card is an ace and the second card is a queen. So we're going to start it off the same way. So we get an ace and a queen. So the chances of drawing our first card as an ace would be 4 out of 52 because there are 4 aces in a deck. Now, because I haven't replaced my first card, I now have 51 cards to choose from, and 4 of those options are queen. So, multiplying those together, I would get 1 over 13, 4 over 51, which simplifies to 4 over 663, which is approximately 0.006. So pretty small chance that you are going to get that particular combination.